Alrighty, welcome. So for the next little bit, this chapter is all to do with uses of exponential models. So we're going to be having a look at some of them. Now, the most common exponential model that we've probably seen is something along the lines of a population model. So P of t is equal to some initial value P to the power of e kt, something like this, where k is some constant, P naught is the initial population, and we can see in this question right here how this formula can be used quite quickly. You'll notice we use the base e. This is despite the fact that using the base e seems a little bit strange because the population is never going to grow by exactly 2.7, but it means that when we need to do calculations with it, it's much easier to work through. Alrighty. So, under ideal conditions, flies reproduce rapidly. After introducing 4 flies to a contained laboratory environment, the following data was collected. The weeks and the number of flies are being modeled here. In this case, using the letter N for meaning the number of flies. Use the data from the table to determine an exponential growth function representing the population of the flies. Evaluate the reasonableness of the model, stating the strengths and limitations. Alrighty, so first of all, let's write our function, our basic function. N of t is equal to n naught e to the kt. Alrighty, and we know that at time 0, at t equals 0, n of 0 should be equal to 4. And so we get 4 is equal to n naught e to the k times 0. K times 0 is 0, e to the 0 is 1, n naught times 1 is just n naught. So we figured out one of our variables. Let's figure out the other one. So the second piece of data here says that when t equals 1, n of 1 equals 4. Oh, not 4, 133. Alrighty, so 133 on the left is equal to 4 times e to the k times 1. K times 1 is just k. If we divide both sides by 4, we get 133 over 4 is equal to e to the k. And to solve this, we're just going to take the natural log of both sides. The log of e to the k is just k. These cancel out. And so then we can work out that k is approximately equal to 3.504. I could definitely go on for longer, but this will do for today. But that was choosing this point here, right? I chose this point, but I actually have another point that I could have chosen. So let's try that one instead. So instead of n of 1 equals 133, let's do n of 2 equals 4,400. Alrighty, we would get 4,400 is equal to 4 times e to the k times 2. Divide both sides by 4 and we'd get natural log of both sides. Natural log cancels with the e. Divide both sides by 2. And we get that k is approximately equal to, is approximately 3.501. Okay, so we can see that with real data, sometimes you have to split the difference. And in this case, we've got two functions that are approximately around 3.50. In fact, both of them to 2 decimal places. We're down to 3.50. And so our final model could be something along the lines of n of t is equal to n naught, which was 4, e, and then to the 3.50 t. So this is our final model. The last part of the question asked us to evaluate the reasonableness of this. Now, for a strength, we know that it is suitable to 2 decimal places of accuracy. Since in both of the 2 substitutions we tried, we got very similar answers. And in fact, they round to the exact same, to 2 decimal places. So that's a strength. One of the limitations would be due to the fact that there's no limit on the population. You would guess that at some point the number of flies would have to slow down, and an exponential model does never slow down. So a limitation is that it does not take into consideration any sort of limits on where the population might stop growing. And so there's just a little bit of thinking about what is the model strong at, and also what isn't the model actually taking into consideration, because we'd actually expect, right, the model would slow down. The current model we have gives us a picture that will look something like this, right, where it starts at 4 and then it grows quite quickly up. What we'd also expect is that in reality it should have some kind of population cap on the far side, and our model that we're currently using does not take that into consideration. Alrighty, so here's just playing around with some exponential models. I'll see you in the next one. Goodbye.